So I'm going to let's go get ready to get started. I adopted the Bell Labs 5-minute rule as opposed to the old Harvard 7 minutes. It's our pleasure to welcome Professor Amir Yacobi, who's giving the third lecture in this series, this Quantum at Harvard series, which we kind of have branded and put together this year. But it's going to be the different incarnation of what's going on quantum-wise at Harvard, because I think for the most part, you're the only person that's doing sensing, right? And I'm not sure why that is, but you're the only person whose group is really focusing on field measurements and probing quantum systems with quantum sensing tools. And so I'll get out of the way and present Professor Yacobi.
Thank you.
I'm not sure. Does he need to use this? Or
No,
okay.
for questions.
Okay.
Well, first, I'd like to thank Ling and Bill for giving me this opportunity to tell you a bit about what we are doing in our group. Largely speaking, I'm hearing some kind of an echo. I want to encourage questions, by the way, so please feel free to interrupt, ask questions as we go along. It'll help, I think, the flow of the talk. Largely what we do in our group is work at the interface between measurement tool development new ways of probing quantum matter, and using those tools to learn something new about the materials. And today I'd like to tell you a little bit about two types of probes that we've been using over the past several years in order to learn a little bit more about quantum materials. And so I think the first thing I'd like to do is provide some motivation, because you might be asking yourself, well, we have a ton of measurement tools. Why do we need more? Why do we need more ways of looking at quantum matter? In effect, our toolbox is very rich as it is. So it turns out that over the past decade, condensed matter physics has challenged us experimentalists with phenomenon that are really hard to probe and to validate or invalidate experimentally. And I'd like to give a few examples. By no means this is a comprehensive set of examples, but just to give you a little bit the gist. So, for example, here on the right, I have what's known as a two-dimensional topological insulator. This is an insulator. It's confined to 2 dimensions, so there is a quantum well here. And in the bulk, there are no states for conducting electrons. But the meaning of a topological insulator means that at the boundary of this system, they're actually conducting states. And these conducting states in a topological insulator carry charge in opposite directions. So these red balls are moving in one direction, the blue ones are moving in the opposite direction, so there is no net current flowing along the edge. What's peculiar about these topological insulators is that the spin carried by the electrons moving in one direction is opposite from the spin carried by the electrons moving in the other direction. And so what this means is that this edge doesn't carry any charge current, but if you think about it, it carries angular momentum, it carries spin current. But as far as I know, today there aren't really any tools that allow us to approach this specimen and say, hey, there is a spin current flowing here in steady state. We just don't know how to probe the presence of a spin current. So this is an example of a challenge for a phenomenon that is predicted to exist in the ground state in equilibrium. Another example here that will highlight a different challenge, this pink thing here is graphene, so a monolayer graphite that is suspended in this device. And it turns out that when you subject this graphene sheet to a strong magnetic field, instead of having all the electrons polarize in the direction of the magnetic field, they actually favor forming an antiferromagnet. Now, we do have tools to probe magnetism, like neutron scattering, and they can probe antiferromagnetism as well, but the challenge is that here there is only one monolayer of material, and the density of spins is about 1 million times smaller than the density of spins that you'd find in a conventional magnet. So a conventional neutron scattering technique will not be able to get enough signal in order to know that the underlying order in this system is antiferromagnetic. So again, we're challenged with the inability to validate or invalidate a theoretical prediction that says, hey, that's the way the system should organize. Now, if you go beyond... Question? No, I'm just hearing myself, I guess. If you go beyond the ground state properties of a material, you can ask, well, what about excitations? Excitations live above the ground state configuration of the system. And here again, just two examples. One is known as spin liquids. Spin liquids are materials that are frustrated, namely the orientation of spins on the different sites can't decide what is the best configuration for them to minimize the energy of the system. And in fact, what's believed to be the ground state of a quantum spin liquid is a superposition of all possible singlets between any pair of electrons on this lattice. So it's a superposition of this configuration plus this, a very, very complex ground state, quantum mechanical state. The excitations, however, above this ground state are believed to be spin-ons, basically excitations that carry spin with no charge. So somehow the spin and the charge dissociate in this material. And the spin excitations behave as fermions. Later in the talk, I'll talk about spin excitations that behave as bosons. Here it's really peculiar. They're expected to behave as spin-ons, as fermions. And again, we don't really have good tools, or there's a need to find tools that could observe these excitations, say they're there, without having any charge, and learn something about their properties, their density of states, etc. Another example are what's known as topological superconductors that can host excitations that behave neither as fermions nor as bosons, but are non-abelian. When you exchange two, the underlying quantum mechanical states of the system doesn't just acquire a phase, it ends up in a different state. And again, we don't really have a good tool set to explore these type of excitations either. Now, once you have well-defined excitations, you can go even further and ask, well, what about their transport? Suppose I have some of these peculiar excitations, like spin waves. Can I create a chemical potential difference to drive a current of these excitations? Can I probe this current? What is the analog of the voltage difference for these excitations? And what is the analog of current? And what are the tools that are needed for doing that? In fact, there are predictions, and I'll talk more about this later today, that certain magnets can condense to form superfluids of their spin excitation. So this thing becomes a spin superfluid and can basically transport angular momentum or spin without dissipation throughout a specimen, throughout a sample over long distances. There are other universal characteristics of transport of spin excitations, for example here, that are also interesting to explore. And again, the challenge is to devise these tool sets in order to be able to probe any of these phenomena that I've discussed today. So I think what's clear is that we need alternatives to conventional simple measurements like electrical measurements or the various scattering techniques. We really need to develop new techniques, and this is something that our lab is focusing on a lot, and I'll talk about a subset of things today. So today I'll only be talking about scanning probe techniques. There are many other types of activities in the lab that are devising new measurement techniques that I won't talk about today. But today I'll talk about only these two probes, basically, that allow us to probe local properties of the material by sensing either local potentials or local magnetic fields. And you might say, well, these are quite limited. We're only measuring a local potential or local magnetic field. But in fact, you'll see that they offer us a tremendous range of possibilities in exploring quantum matter. So at this point, I'd like to pause and really, in the spirit of developing a measurement apparatus, I want to ask, really, what do instruments measure? And let's take an example, because I think this is not something that's very, not everybody is thinking about this every day, but suppose we take, global positioning systems. So they're obviously reporting a position. They're telling us our position with high accuracy, but what are they really measuring? What does your GPS measure in your car or phone?
Radio signals, I believe.
So what is it really probing? I mean, it's telling us our position, that's for sure. That's what it's reporting. It's measuring an RF signal, but what's the information that's used in order to derive?
Distance from a satellite.
How is it telling us the distance from the satellite? Are we measuring, is it a ruler that's taking us from us to the satellite? What is it doing?
It's a constellation of 4 satellites that does the atomic clock synchronization.
Okay, but what is the signal that we're kind of using to derive the
Phase differences?
time, right? It's basically the time it takes the signal to go from the satellite to our phone. Different satellites are different location. From knowing that time, we can deduce what the position is. But in fact, this connection between the time and the position is really complex. It actually involves general relativity. So in order for us to succeed in predicting our location accurately by measuring time, we need a piece of physics that we understand very well and that allows us to connect the quantity that we know how to measure and the quantity that we want to report. And this is kind of a general theme that any time you have some cool piece of physics that you've figured out and you know how to measure one quantity that appears in this physics allows you to connect what you know how to measure, perhaps to report something new. And this is what we're using over and over again in devising measurement techniques, and I'll give you a few examples today of this process. All right, so the first technique that I want to focus on, and I'll only give 2 examples with each technique, is basically a sensor that is a tiny defect in diamond known as nitrogen vacancy center. You can think of it as a spin quantum bit, but it's basically a 2-level system, one spin that we know how to control very, very effectively. And what it allows us to do, and I'm not going to go into the detail of how it does it, but what it allows us to do is measure locally the magnetic field as a function of frequency in a relatively broad range of frequencies from DC to a few gigahertz. The way it does it, it's basically a 2-level system. It's just a spin. And the way it does it is a magnetic field induces precession of that spin. And by measuring how much the spin precesses, we can tell what the magnetic field is. This would be a DC measurement. And then there are ways to operate this system in a way that will tell us what the alternating magnetic fields are in a broad range of frequencies. So you might say, well, this is kind of a very simple quantity. How can it teach us about many different things? So what these arrows are showing are different connections, different pieces of physics that basically connect what we know how to measure with what we know how to report. So in this example, we know how to report by measuring these magnetic fields. We can measure the spin density in 3 dimensions, basically perform a magnetic resonance imaging measurement in 3D to report the spin density of free spins, uncorrelated spins, in space. In this example, we're measuring magnetic fields as a function of time, but reporting the local magnetization. And these are magnetization textures that you can find in certain magnetic materials. These are known as skyrmions and are very interesting candidates for storing high-density classical information. And it might seem simple to connect magnetization and magnetic field. We know through our classes in electricity magnetism that they're connected. It turns out that there are actually an infinite set of magnetizations that produce precisely the same magnetic field patterns. So the challenge is to distinguish which one is the right one. Another example is using measurements of magnetic field to determine a quantity that characterizes superconductors, known as the superfluid density or stiffness. And again, there is a piece of physics that we understand to connect these two. I'll talk about the measurement of spin chemical potential. So in certain magnets, you have excitations. These can be described by a chemical potential, just like a voltage for electrons, but this time for spin, and we know how to measure that. We can measure current flow patterns. This is the current flow in graphene, for example, showing something that's called hydrodynamics. It turns out that electrons behave very much like a fluid under certain conditions. And lastly, I'll give an example today of how to measure basically the magnetic susceptibility response function of a material to magnetic perturbations using what we call a Magnon scattering platform. So I'll focus with this technique only on 2 examples out of these many. But the point is that there are many pieces of physics that once we figure them out, allow us to report very interesting physics by measuring a simple quantity. All right, so let's start with the chemical potential. So I already mentioned the notion of spin superfluid. So in a magnet, the spins can fluctuate, and they would form spin waves, just like wheat in a field pushed by the wind. Each plant pushes the other, and they're basically just moving nicely in the wind. This is how magnons can be envisioned. And as I mentioned, these ideas of spin superfluid transport appear to be fairly new, 2014. But it turns out that it's actually a very, very old topic. So this is a paper by Bert Halperin, our own Bert Halperin, and Pierre Hohenberg, titled Hydrodynamic Theory of Spin Waves, where the first sentence in the introduction, in the abstract, is a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two-fluid hydrodynamics for liquid helium. So you all know liquid helium is a superfluid. Well, it turns out that they established a very rigorous connection between superfluids and spin waves in magnets, and it turns out that it's actually quite general. There are many, many magnets that should have this property. And the reason it's only now that people are getting kind of, again, excited about this field 50-some years later is because we're just now starting to have the tools to really explore this kind of superfluidity in these systems. So, to give you a sense of what these spin waves are. So here are my spins. And a spin wave corresponds to this precession, let's say, of this spin around some magnetic field or anisotropy, and there's a phase lag between these different spins, and it produces a wave. And these waves have a dispersion, so there's an energy to these spin waves, and there's a momentum, and typically if the interaction between the spins are nearest neighbor, it's going to be quadratic. Because there is a magnetic field on, it turns out that spin waves cannot exist below a certain energy. And that energy is given by the Kittel law here, which follows some square root law. And the law is not so important, but what I want you to remember is that there is an energy gap here below which you cannot have any spin waves, and above which you can have spin excitations inside this material. So what is a superfluid? What are the characteristics of a superfluid then? So if I have Bose excitations, and these spin waves are bosons, just like what we need for a Bose-Einstein condensate, what characterizes a Bose-Einstein condensate is that as you increase the number of excitations in the system, the chemical potential in the system would rise, but once the chemical potential hits the lowest possible energy state in the system will level off. The chemical potential will not rise anymore because we're going to start having macroscopic occupation of the lowest state. So the system will basically form a macroscopic coherent population of one particular state, the lowest possible state, and the chemical potential will saturate. So if we had a tool to measure chemical potential, this is what we'd expect to see. We'd expect to see the chemical potential rise and then saturate precisely at the value corresponding to the spin gap in the system. And again, please ask questions. Okay, so how can our sensor, magnetic field sensor, help? So as I mentioned, our sensor is a two-level system, and it's a spin, so magnetic field fluctuations can couple these states if the fluctuations are precisely at the frequency or energy corresponding to the difference between these two states. And so at any given temperature or density in this magnet, I have these fluctuating magnons. They correspond to fluctuating magnetic fields. And we're going to be sensitive to those precisely at the energy of the NV center. So in essence, what the NV center is telling us is how many of these spin excitations exist at a particular energy. And it turns out that that's enough to determine what the chemical potential is. Yes?
Could you explain again why the chemical potential saturates at this spin gap?
Yes. So, fermions are particles in which you cannot put more than two in each state because, for spin up and spin down, and that's it. They are always, fermions are indistinguishable and they don't like each other, so you can't have more than one or two electrons if you have spin in each quantum mechanical state. Bosons are the other creatures. They like each other. you can actually put many in the same state. And in fact, when you're increasing the number of particles, energetically it's favorable. You see that chemical potential is like a penalty, right? If you raise the chemical potential, you have it's energy cost. Well, the system, as you're increasing the number of particles, can basically just put more and more of these particles in the ground state here without paying more energy. That's beneficial, and that's what the system does, and it actually forms a coherent state that's described by a macroscopic wave function. It has many, many interesting properties. But for us today, what's important is that the chemical potential saturates. So as I mentioned, what our NV center is able to measure is the number of these magnons at the particular energy that the NV center is probing at. And from that, because that number depends on the chemical potential, you see that there is a relation between number and chemical potential. If we can measure the number, we can determine the chemical potential. And so when we analyze our data based on this understanding, what you can see is that the chemical potential, which is the vertical axis here, as we're increasing the number of particles here, rises and then it saturates, flattens out, and it flattens out precisely at this boundary here given by the Kittel law. And note that this shape here is precisely what I've drawn here. So we're really measuring the chemical potential of these excitations by understanding the physics that connects between spin fluctuations, their number, and chemical potential, and reporting the chemical potential, which basically shows how the system behaves very much like a Bose system, where the chemical potential flattens.
Sorry, I'm a little bit confused. Like in the picture that you just showed earlier, it looks like that you care about the excitation at the ESR frequency higher than the minimum of the band. But here you're also saying that the chemical potential is just when you hit that minimum. Then are you looking at the minimum or are you looking at the excited?
Right, so the fact that the chemical potential is below this minimum, let's say at this energy here, does not mean that you don't have any excitation. The chemical potential at any finite temperature is not, there are excitations above the chemical potential and below. It's a number, but at any given temperature, you're going to have particles living at higher energies than that and ones at lower. We're sensing the ones that live higher at the energy up here, larger than this gap, but it informs us where this chemical potential is. It could be somewhere here, it could be very far below, but it won't rise above this number here.
I see, thanks.
So again, in the scheme of things to describe how to measure various quantities, here the quantity that actually enters is something from statistical mechanics known as the fluctuation dissipation theorem, and it allows us to connect magnetic noise, which is what these magnons are producing, with the spin chemical potential, which is a quantum mechanical quantity describing a gas of particles. An example that I'd like to give with this, what we call a magnon scattering platform. And so let me just review for you what scattering experiments do. So generally speaking, if you think about a scattering experiment, like light scattering or X-ray, you have some material, and you shine some radiation or particles on it. This could be neutrons, these could be light. This light is propagating in vacuum, and actually very useful that it's propagating in vacuum because we know its properties in vacuum. It then impinges on the material, interacts, something very complicated happens here, and then it diffracts, again in vacuum. And the scattering experiments measures what happens far away, not in the complicated region. It measures things far away. And by measuring the amplitude and ideally phase of the scattered waves, one could reconstruct what's going on in the material. That's how X-ray works. X-ray scattering, we can reconstruct the structure, etc., etc. Neutron scattering constructs the magnetic properties. But the idea is that we're not focusing on the interaction region itself, which could be very complex. We're looking far away. So we were interested to see, well, again, here, as I mentioned in the introduction, there are challenges, right? If I have materials that are only a monolayer, I can't really operate the conventional scattering technique. So can I devise some sort of scattering techniques that will teach me something about, let's say, the magnetic properties of materials, but when these are a monolayer and are only a micron size. So this is what we came up with. What we have here is a slab. This is a slab of a magnet. It's about 100 nanometers thick, made of a very high quality magnet known as YIG. YIG is the star of magnetic materials. It can support spin excitations that are very, very long-lived. They can propagate over millimeters without decay. This is what I'm going to call our vacuum, because spin waves do not exist in real vacuum. I really need spins. So this is our vacuum. We understand fairly well how spin waves propagate in this medium. Our target is going to be placed on top of this vacuum, situated here. In the experiments I'm going to show, it's going to be another piece of magnet, a different type of magnet though. And using electrical control, we can generate spin waves in our magnet. And the way we do it is by sending alternating current in this wire here, in this antenna. This generates alternating magnetic fields, which then start to wiggle our spins and launch spin waves. The frequency of these spin waves is set by the frequency of the current in the antenna, and their wavelength is dictated by the dispersion of our vacuum. So once I know the frequency, I have a wavelength. And so the idea is to use our sensor, this NV center, this magnetic field sensor, to measure these spin waves after they've scattered off of this target, and to reconstruct from that what caused the scattering. I'm not going to go into great details, but the way we do that, in fact, we can measure both amplitude and phase of the scattered waves. So these magnons in the region, let's say before the target, they're just plain waves. And they're propagating, they're moving waves, they're moving fronts. They can be characterized by some omega and some k, as I described, but they're generating a time-varying magnetic field. As explained before, NV centers are really good to measure time-varying magnetic fields. So we can pick up the signal very, very clearly as a function of position. If we wanted to know the phase of this time-varying magnetic field, we need a reference signal. And that reference signal is sent by another antenna that sits far away that in effect only affects our sensor. And it's the interference of these two that allow us to extract both amplitude and phase. So when we do this, these are, for example, an image of these wave fronts propagating through the sample. Their wave length here is a few micrometers. At the frequencies that we are operating. And you can see that before the target, they're very nice and straight waves, just parallel to the antenna that generates them. But we can now change the frequency to extract the dispersion of these waves. So this is wave vector and energy. We can read it off directly from this kind of measurement. If we now turn the reference signal off, and we're only measuring the amplitude, this is what we see. So this white circle is the target. Plane waves of these spin waves are impinging on this target, they're diffracting, and you see that we get a kind of a diffraction pattern somewhere in the far field. If we were to now add the reference signal, now we can pick up phase, and it's the combination of amplitude and phase that allows us to reconstruct what the target was, what is scattering our spin waves. And I'm not going to get into detail. It turns out it's actually a very, very complex process. And the way we do it is by proposing a target and generating from that target what the scattered spin waves, the phase and amplitude would look like. And if it doesn't agree, we're going to modify the target until we get better and better agreement. And so this just shows the iterative process. And I don't want to say too much about what exactly is scattering these spin waves, except for the fact that it's basically the response function of this target to the impinging spin waves that's generating this kind of diffraction pattern. So we hope that this is going to be a platform that allows us to position many different materials of interest and learn about their properties by doing these kind of diffraction experiments, but this time with spin waves. Before I move on to the other measurement probe that we have that measures electrostatic potentials, let me see if there are any questions about these examples. Yeah.
A quick question. In this experiment, what is the target
The target is permalloy. It's a very thin disk of permalloy. So our vacuum is YIG, is the one that we understand well, and here we just put a different magnet on it, and we see the diffraction of the spin waves. It's a much stiffer magnet. Permalloy is a much stiffer magnet than YIG, and it's basically kind of not allowing the spins to fluctuate so effectively in its vicinity compared to what the YIG is able to do, and that's what producing the diffraction.
Roughly speaking, the spin wave kind of go around it, couldn't penetrate it. Is that how I...
You can think about it that way, yes. Basically, they're kind of locked in place there. But in fact, if we put a copper piece per disk, something non-magnetic, we also see a diffraction pattern. So it doesn't have to be a magnetic material. And you can see why, right? Because the varying magnetic fields associated with these spin waves, if you have a metal disk now, will generate currents because of Faraday's law. And these currents generate magnetic fields themselves that drive new spin waves and produce a scattering. Yeah.
Yeah, Emil. So the MV center you put it there as a probe, and it also will cause the scattering or not?
No, so the NV center is very inert. It's made of diamond. Our sensor itself is one spin. So yes, in principle, it could cause a perturbation depending on its orientation, but its effect is extremely, extremely weak. In fact, if we can make it very strong, it would be very interesting. We don't know how to make that interaction very strong. But so the back action of the sensor on the system is minute. Yeah.
Yeah. So my question is, when you take these images, is it that you scan the probe over each of the pixel, you pause there and you measure? And
Yes.
first, what is the measurement that you do at each pixel? Is it just looking at the ODMR spectrum, or is there any relaxation? And second, what is roughly the time taken to generate one of this image?
Right. So yes, in effect, what we are measuring is ODMR. That's telling us about the occupation, the orientation of our sensor spin, from which we infer what the local magnetic field or time varying, the amplitude of the time varying field at each location is. So yes, you're right, we're scanning. In principle, you could do this also in a CCD form if you had many NV centers spread around, but that technique will be limited to the optical wavelength. Here we're in principle limited to the distance between our NV and the center, so we could have better spatial resolution. The time it takes to collect one of these images is hours.
Quick question. Is the MV center measurement AC in this case? Like, because you have alternating kind
yes.
of
So
magnets.
what the up is the time varying magnetic field. So the nice thing about the NV center is, as I mentioned in the beginning, it can probe magnetic fields all the way from DC, so static magnetic fields, to magnetic fields fluctuating at high frequencies. So this is an example of a magnetic field that's fluctuating at the frequency of the spin wave that we're generating, and we can pick up that signal very effectively by applying the correct pulse sequence to do it.
What are the time and the length scales over which the magnons and YIG are coherent? And kind of in another system, kind of where are your measurement limits given the time and the length scales for magnons and other systems?
Right. So, this is a question that I think is still being investigated, in fact, today. But largely speaking, magnons with not too short of a wavelength can propagate millimeters without losing their coherence. As you choose magnons with higher and higher energy, shorter and shorter wavelength, they have more pathways to relax through magnon-magnon scattering. So as much as we'd like to think about magnons as real particles, in fact, they're interacting particles. And through magnon-magnon scattering, they would relax. They would basically break up, produce more magnons, etc. Exactly how long and how far would these higher energy magnons live is an area of study. Yeah.
What's the propagation or speed? What's the propagation speed?
Yeah, it's about
through this type of material?
1,000 meters a second. Like the speed of sound in solids. It's fairly fast.
Not the speed of light. So.
Not the speed of light. Okay, so let's move on. Okay, again, just a summary. This is basically spin wave theory connecting magnetic structure factor and what we know how to measure. All right, the second tools that we're developing or have been using, I would say, is a local charge sensor, or local potential sensor. And I'll explain a little bit how it works. And again here, even though this is just, we're measuring the local potential, you can think of it, okay, what's the voltage at this particular location that we're measuring within 1 meter resolution? It turns out that, again, there is a very large set of physical phenomena that we're able to connect to this measurement by knowing the relevant physics to connect them, or discovering that physics. Just a few examples. I'll talk about the measurement of fractional charge. I'll explain what that is. I'm going to skip that one. This is a measurement of phase transition. So it turns out that materials can undergo phase transitions, for example, from an antiferromagnet to a ferromagnet. If I apply a very large magnetic field, eventually an antiferromagnet will choose to become ferromagnet. Measurement of potential, for some reason, is able to demonstrate and extract these phase transitions very, very precisely. These are these dark blue features that you see in the slide. Recently, over the past year or so, we were able to measure with this electrostatic technique how electrons bind to spin waves to form what's known as skyrmions. So these are spin textures that look like hedgehogs. And the other topic that I'll talk about today, in addition to the fractional charge, is the local Chern number. I'll say more about that. It's basically measuring topology. It's measuring something very geometric in a material, and we're able to extract that information by measuring potential. So how does it all work? All right, so a little bit about the sensor. So you can see here what the sensor is. It's basically a small metal particle, about 100 nanometers in size, connected weakly to 2 electrodes. So schematically shown here, 2 electrodes, the blue, and a small metal particle in the middle. There is no current flowing between our tip and the sample. The only current flowing is from one electrode to the other. It's all in the probe. So it's a very non-invasive probe. This is not a scanning tunneling probe, okay? Basically a device like a transistor, it's in fact called a single electron transistor, that is mounted on the tip. So this quantum dot, if there is some local potential that we'd like to pick up, you can think of this configuration as a capacitance. And we know what the energy of a capacitor is. The energy of a capacitor as a function of the charge is quadratic. Q squared over C. Now, the interesting aspect of this device is that because it's weakly coupled to the electrons, this is a metal electrode. It can have 1 billion electrons or even more. Many, many electrons. But it's an integer number. It's not going to be a half integer of electrons because electrons come in units. So this is an integer number of electrons. So when I look at this energy versus charge, I actually have to look only at integer values, n, n plus 1, n minus 1. And you can see that depending on this voltage, there are going to be 2 typical configurations for this sensor. One in which the minimum energy is indeed n electrons. So then the system is happy. It has n electrons. But you can see that if an electron wants to go in and out, it has to change the charge state. It has to go from n to n plus 1, let's say, and back to n. But if this particle is small enough, this energy difference is going to be too large at the temperature we're working, and the current is going to be suppressed. This process is going to be suppressed because the charge is quantized. But if I change this potential by a little bit so that the minimum energy wants to be at n plus a half, it can't, but it wants to be at n plus a half, then the system is ambivalent. You see its energy for n electron and n plus 1 electrons is precisely the same. Now there's no penalty to take an electron, put it on the dot, and remove it. There's no energy cost associated with it, and current will flow. So you see tiny changes in potential that only induce fractions of an electron on this particle can be easily sensed by monitoring the current through this device. And it's called a single electron transistor because this curve goes on and on each time you add one electron. So it's periodic in the number of electrons. In fact, you can think of it as an electrometer. You can count electrons one by one by doing it. But if you just position your sensor somewhere here, you see it becomes extremely sensitive to tiny, tiny changes in potential. So just some numbers. Voltage sensitivity is 1 microvolt in 1 second. If you translate charge sensitivity, you see we can actually detect tiny fractions of 1 electron, 10 minus 4 of 1 electron. You can ask yourself, well, why is this useful? Nature doesn't have 10 to the minus 4 of an electron. Well, the point is that when we're trying to measure a charge, we're not picking up all the electric field lines emanating from that charge. We're only going to be picking up a tiny, tiny number. So we should be able to detect much smaller values of 1 electron to say that there is an electron, because a lot of the field lines are just going to go somewhere else. And spatial resolution, about 100 nanometers. We can push it down, but it's roughly 100 nanometers. All right, so first example is measuring fractional charge. So where would we, in fact, encounter or expect to see fractional charge? So this is already a peculiar. I was just mentioning that charge is quantized. Electrons comes in units of 1e in nature. So where would we see fractional charge? It turns out that when you subject an electron system that moves in a plane, a two-dimensional electron system, to a strong magnetic field, it can develop under certain conditions a fractional charge. So before that, let's see if we can detect integer charge. So what happens in the bulk, these electrons are seeing the strong magnetic field. They're just moving in circles, so they're localized. And this is known as the quantum Hall effect. I don't want to go into great details into it, but one of the interesting things about it is that it has a Hall conductivity such that when the Fermi energy is in the gap between the quantum mechanical levels that describe the system, known as Landau levels, the prefactor here is an integer. And it's called a Chern number, and I'll come back to that with a second example. But what's most important is that all states in the bulk are localized, and if I now ask, well, when I change the density in the system, how will the number of electrons in the bulk change? They're going to change one at a time. So if we position our sensor somewhere above our sample, and here is just a depiction of some disorder landscape to indicate that there are regions of lower potential where electrons would like to accumulate versus other regions. And we scan along a line. So this is the position, and this is density. And these dark features here are signatures that our sensor picks up when an electron hops in. So what you can envision here is when we're raising the density, at some point we hit this black line, an electron pops in exactly at this position. And then at some later voltage, another electron pops in that position, and it's just one electron. And then we continue, and then the second electron hops exactly into that position, and then another one and that one, and a third one here, and the process goes on and on. And we can image this in space, and we can really see very nicely where electrons are added. And these are integer electrons. So now we can ask, well, suppose we change the conditions in the system, and it turns out the only thing you need to do is put your Fermi energy within the band. Coulomb interactions in the system give rise to a new energy gap that creates a very interesting state known as the fractional quantum Hall effect, where this integer is no longer an integer, becomes a fraction. But the system is still gapped, so all states are localized. And now, if the potential, this order potential, is exactly the same as before, but just the charge unit has changed, well, let's see what happens. So our electron broke up into 3 pieces, according to theory. We're going to fill up exactly the same landscape and move along exactly the same line, and this is what we see. So what we see is 3 times the number of charging lines. Suggesting that now the way charge enters these charge pockets is 1/3 of an electron at a time. So this is quite surprising because, again, 1/3 of an electron doesn't exist in nature, but exists inside the solid. And you can really, it really has a physical meaning to think about these 1/3 charges. In fact, if you under certain conditions in any integer filling factor, so when the Hall coefficient is an integer, 1, 2, or 3, you see exactly the same image. And when you measure when the Hall coefficient is a fraction with a 3 denominator, you get 3 times the number of lines, indicating that the charge unit is indeed E over 3. So by simply measuring potential, we're able to deduce that the system hosts fractionalized charges. The piece of physics that goes here is exactly the same physics that describes how our SET works, which is Coulomb blockade. Yeah?
What about 2/7?
So 2/7, the charge is 1/7.
Okay.
And it's very hard to measure because it's a very small unit of charge. We did do measurements at 5/2. 5/2 is a very interesting fraction because it's an even denominator. And it turns out the elementary excitations there are E over 4. And that we were able to see. So you can see E over 4 at filling factor of 5/2. But yes, actually, yeah. And but yes, the smaller fraction, kind of the bigger the denominator, the smaller the unit of charge, and it becomes just harder and harder. But I think generally that's what we're seeing. Yeah.
Well, when you say 1/3, for example, does that mean that 3 traps will be filled up at the same time, or just one trap? Did you truly get 1/3? What does it mean?
It's truly 1/3. So, okay, if I were to try to pull 1/3 of an electron outside of this layer into vacuum, it'll grab 2 other thirds and construct an electron. There's no way to pull it out. But inside this material, 1 electron decomposes into the 3 constituents, and these 3 constituents are completely free from one another. So when we're doing this experiment, we're trying to change the density locally in that pocket. So what happens is we are bringing from somewhere, just like when you're charging a capacitor, you're bringing charge from infinity. We're able to bring 1/3 of a charge into that region and then bring the second 1/3 and then the third, but it's all within the material. It is physically split up inside the material.
Do we have the in this system? Do we have 2/3 states, and what we expect to see?
So 2/3. This is the case of 2/3, and this is the case of 1/3. It turns out that both of them have 1/3 charge. So what determines the charge is just the denominator. It's not the numerator.
So I guess the question I would ask is, does this? I mean, you're not really splitting up an electron. You're kind of looking at the wave function in a wacky way, right? I mean, you're kind of imaging a part of the wave function. Is that a better way to think about it?
Well, I'm imaging the charge associated with the wave function. That's certainly correct. But the whole point is that basically what happens is that, right, think of phonons, basically sound waves in a material, right? If you want to describe the excitations of a solid, you're not going to describe the motion of each atom, right? You're basically going to say, hey, I have this wave of atoms, like a guitar string, and that's the lowest mode, and then the second mode, etc. These are the elementary excitations. The elementary excitations in these systems are these fractionalized charge. Each one of these E over 3 is constructed of many, many electrons in the system in a very, very complicated wave function. Very, very complex. The Nobel Prize was given for writing down this wave function. It's a very complex wave function, but the end result is that the system is behaving as if it has independent particles that have fractionalized charge.
Is the 1/3 value inherent, or is it just what you used as a test?
No, 1/3 is the fundamental unit of charge in this state. And as Bob was saying, if you go to a different filling factor, so all the interesting filling factors that have gaps in the system for which this idea is valid would be odd denominators typically. So you would find, let's say, a 1/5 charge, or like Bob was asking, a 1/7 charge. Even denominator states could have peculiar, it's much harder to understand. They resemble superconductors more than they resemble conventional metals, but they could have even denominator charge, like E over 4.
Can you say something about how the sensitivity of your measurement in general depends on the structure of the probe, how big the quantum dot is, things like that?
Right, so here we're using the natural disorder in the material. And luckily, the size of the pockets in which charge settle in are comparable to the size of the tip. In what I'll be talking about next, which is twisted graphene, there the unit cell is about 10 nanometers. We're going to be obviously looking at many, many unit cells. We don't have the spatial resolution for that. But it would be nice to develop probes, and I'll say a few words about new probes that we're developing towards the end, that would allow us to sense maybe things with a much higher spatial resolution. I think there is a demand for it. We don't really know very easily how to do it.
On the maps, like just the integer ones, is like different, so some lines are darker, some are lighter. Like what's the difference?
Right, so this is basically the intensity of the signal that we were picking up. So here this line is much stronger, and here it might be that there are quite different conditions between this measurement and that. The magnetic field from here to here tripled. And our sensor, we want to believe that we're scanning precisely along the same line, but if it moved a little bit in some direction, then we might be picking up this dot a little bit weaker, etc. It also depends on, so I mentioned that the electric field lines from these charges are not all terminating on our tip. And so you can think of it as screening. In fact, if you think about the geometry, it's a little bit peculiar. So we have the system of interest here. We have an electrode below it, which allows us to change the density. And we're looking from above to see how the density is changing. Now you know that in a capacitor, there are no electric field lines that should appear outside. All the electric field is contained between the two plates. And yet this entire technique relies on the fact that there are some electric field lines peeking out of the top plate. And these are quantum effects that would not exist in a classical system. And that's what this technique is really based on. Okay. Last example, I hope you have a little bit more stamina, is the measurement of topology. So I already argued that when you subject the system to a very strong magnetic field, it has a Hall conductivity. You send current in one direction, you measure voltage perpendicular to it, and in some units of universal constant, the coefficient here is an integer. And this is a geometrical requirement. There is no way to get something else. It can't be an arbitrary number. It can be 0, 1, 2, 3. It can't be anything else. It turns out, and this is the lesson that we've been learning since the beginning of 1980, the Nobel Prize in Physics on topology, that if you have periodic potentials, some artificial potential, like in a lattice, but you don't have any magnetic field now, it turns out that you can generate a transverse conductivity like this just from a periodic potential, even at zero magnetic field. I'm not going to describe why. It has to do with the geometrical properties of the bands that are generated by the periodic potential, but it's a very interesting result that gives you a universal integer constant. Now, this constant could be 0 also, but when it's not 0, it's very interesting. And in twisted graphene recently, this is what has been seen. You take 2 sheets of graphene, you twist them by roughly 1 degree, and the system exhibits transverse conductivities that have a coefficient that's not 0, at 0 magnetic field. Now, we already saw that fractionalized charge appears when this coefficient is a fraction, 1/3, let's say. And this is allowed once you have interactions. Why is that allowed? It's complicated, but it's allowed. And the question is, can we get these fractionalized excitations now at 0 magnetic field by just having a periodic potential? So what I'd like to argue is that with our sensor, we can measure this coefficient. So it's essentially saying we can measure conductivity by measuring the local potential at one point without sending any current through the material. So how does that work? So the way this works is based on something that's known as the Streda formula. What the Streda formula says is that if you have your Fermi energy in a gap, so you have a bunch of filled bands, it's in the gap. What's peculiar about having a coefficient here, C, that's not 0, is that the number of states in the filled bands changes with magnetic field. This is not the typical thing. Usually if you have a band, you're applying a magnetic field, weak magnetic field, the number of states is not going to change. But if this coefficient is not 0, the number of states is going to grow with magnetic field in a proportional way precisely given by this coefficient C, where phi naught is again just some universal constant h, Planck's constant, divided by the charge of the electron, h over E. So this is a very, very interesting result that gives you that in order to maintain the Fermi energy in the gap, when I'm increasing magnetic field, I need to change the density in the system because the number of states is changing. Okay? Again, let me repeat this. I have a band, I'm changing magnetic field. If I don't change the density in the system, my Fermi energy is going to go into the band because suddenly I have more states. I need to fill up the gap, the band, to be in the gap. And this is one example. So you see density on the horizontal axis, magnetic field on the vertical. Bright signals is what we know how to measure. Turns out that this technique can easily measure energy gaps. And you see that in order to follow the energy gap, we need to move it a diagonal here. And the ratio of this magnetic field to density with this coefficient is precisely 4. So this is a band that has a Chern number of 4. So we're really measuring the transverse conductivity in this system, just measuring local potential, not sending any current through the system. In fact, when we do this on twisted graphene, this is what we see. It's a very, very, again, magnetic field density, very, very rich spectrum of these Chern bands. If I were to distill all these slopes, you see that they're all either integer slopes, which resemble the example that I gave in the beginning of integer charge, which are labeled here with red, that have fractional slope. These are fractionalized excitations. These are systems in which fractional charge exists. And you see that there are quite a few of these, many of which we don't really understand. So here we know how to measure these Chern numbers, these integers or fractions, but we know in addition to say very little about these states. And so this is kind of our going forward task, is how can we learn more about the various states? It's so rich, you're changing the density, the system undergoes so many transitions to different phases of matter. But we know, except to know what their Chern number is, we know very little about them. So this is really what we're pushing for right now, is to develop even more sophisticated techniques that will teach us more. So just in the last 3 minutes maybe, tell you a little bit about where we're headed with that. So up to now I've described separate sensors of magnetic field, a sensor of electric potential. In fact, what we're developing now is like a Swiss Army knife. It's basically a probe that you can turn on any sensor you like, and they're all embedded on one tip. So we're creating these non-planar surfaces, all done within CNS, and fabricating on these non-planar surfaces, on these pyramids. They're roughly by 1 micron on the top surface and maybe 1 micrometer height. So this is an example of a single electron transistor, a charge sensor. This is a squid that will measure magnetic field locally. This is a high impedance resonator, which would allow us to measure AC conductivity. And in fact, any device that you have in mind, we can integrate onto this probe very effectively. So it's a very universal platform. Another advantage of this platform is before all the probes that I described were made, almost one by one. I mean, the NV centers, we can make many of them at once, but the single electron transistors, actually, we're making them one at a time. This is going to be more of a parallel process. We're going to make probes in multitude, and we can get many of these produced in one fabrication cycle. In addition to putting on sensors, we can put gates. So instead of having to fabricate on the device, which might destroy or degrade its quality, we can put our gate sets on this tip, on this pyramid, in a way that now allows us to scan our gate set and look for the nicest, cleanest area so that we're forming, let's say, a quantum dot, and we can sense what the behavior of that quantum dot, again, using a sensor sitting on the tip. So it gives us huge flexibility. Just to see how this thing integrates, so this thing is kind of on a micron scale. It sits, or it's made out of a single silicon wafer, 0.5 millimeter thick, that then gets etched very deeply, because if we have a very large silicon platform only sticking out 1 microns, the angular tolerances that we would need are going to be tremendous. So we have this deep etch. This also allows us to take all the sensor wires down to a place where then we can mount this chip onto a tuning fork made of quartz, again made in CNS, and bond the wires down to extract them into the microscope. And so this is all custom made. You can see this tuning fork with a sample in the pyramid at the end sitting on these homemade tip holders, and then specifically made sample holders that would allow us to bring microwave frequencies, DC signals, etc., and all sitting within a scanning probe microscope that is currently being finalized and hopefully will be delivered in about a month. So with this, I'd like to pause, thank all the group. This was kind of an overview of half the activity of the group, so everybody contributed, many collaborators as well, and see if there are any questions. Thank you.